Okay, we are recording. And let's see, let me call up the chat so I can see if anybody asks any questions. Could I do the first added problem in the review session? Okay, I just printed those off, except I didn't let's see, I didn't blow them up very large. Maybe you can still read them, I don't know. But anyway, we have 1 mole of air and oh man. When I copied it and pasted it in here, um, what was supposed to be in these parentheses, it was supposed to say C sub V is equal to 5/2 R. I don't know if that was the mystery thing or not, but that's the way it would work anyway. Anyway, it's at 301 Kelvin and confined in a cylinder under a heavy piston, and it occupies a volume of 5 liters. Determine the new temperature of the gas if 4.40 kilojoules of energy is transferred to the gas's heat. And so we're told that, I hope this is the problem we meant, Q is equal to 4.40 times 10 to the third joules. And that heat will equal N C sub V times delta T. So this is a molar heat constant. It's the number of joules per mole Kelvin is what that happens to be. And it's actually equal to 5/2 R, and R has units of joules per mole Kelvin. So N is the number of moles. These are possibly new units for some of you, and so we'll have that. But we can actually calculate the temperature change as a result of this. And so delta T will end up equaling that 4.40 times 10 to the third joules divided by NC sub V, and N is 1.00 moles, 1.00 moles. And then it's air, and air is a diatomic gas. Something I wanted to do was show you the formula sheet. I don't know if I printed that off or not. But anyway, in this case, it's 5/2 times R, which is 8.314 joules per mole Kelvin. When I showed you this problem the other day, let's see, I think it said determine the new volume of the gas, and there isn't a way that you can do that. And if it's under a heavy piston, that was supposed to be code for kept at constant volume. And anyway, I'd mistyped I think I'd said new volume of the gas, mistyped that when I put this in here. But anyway, now it's fixed. So we've got that. This is C sub V, there's the N. And so it's a matter of plugging into there to get the temperature difference. And then you just add that temperature difference onto the 301 Kelvin. I'm a little curious just what it might be though. Times 2.5. Okay, and I get a temperature change of about 212 Kelvin. And that's the size of the temperature change, and you just add that on to 301 Kelvin to get the new temperature. And it looks to me like 513 Kelvin will be the final temperature. Okay, let's see. Any other messages or out loud questions? You can unmic yourself if you want to. This test had some other questions on it, but I think I took the ones out that would have been unfamiliar. This problem actually had an A, B, C, D, and E, I think. Maybe that many parts, or it had several parts anyway, but I confined it to this question, which has to do with the first law of thermodynamics. So, oh, and you can ignore that, assume three significant figures throughout, because on this question, all you're asked for is the sign of the quantities, I think, and for the entire cycle. So you don't need to calculate. But the other parts that I cut off that were things that we haven't gotten to would have involved significant figure calculations. Let's see, problem one on the review test. Okay, average translational kinetic energy of nitrogen molecules at 375 Kelvin. Okay, well, the don't have it on top of my head, but this is the average translational kinetic energy of molecules. This VRMS is a type of average, and so that is an average value there. And it's 1/2 mass times the speed squared, and it happens to equal 3 times K, and I'm putting a subscript on the bottom of that. It's Boltzmann's constant. And I do that because in this same unit, we've had coefficients of thermal conductivity, and those are just a K without a subscript on them. So don't confuse those two. We'll look at them in completely different contexts. Anyway, this is all we have to do to calculate that average translational kinetic energy. The stuff in parentheses here is a bit of a distractor for this problem because the only thing we need is the stuff on the right. And so you'd have 3 times Boltzmann's constant, which I just printed off, I think. Maybe. Nope, I didn't. Oh, it's on the front of the test. Let's see. There it is. 1.38 times 10 to the minus 23rd joules per Kelvin. So 10 to the minus 23rd joules per Kelvin. And that's the K. And then the T in this case was 375 Kelvin. So kind of a mess, but that's all you have to do to get the average translational kinetic energy. You don't have to do anything over here yet. So for the first part, it's just going to be 3 times and it is 1.55 times 10 to the minus 20 joules, okay, which isn't much. Actually, for problems of this type, we're not going to, but you might actually use, whoops, 10 to the minus 20th. You might use different units of energy, like a common one for things at this scale might be electron volts, or maybe mega electron volts or something like that. But still, that's the answer that I'd be looking for there. And then it says, what is the RMS speed of the nitrogen molecules? Well, we can take this equation right here and solve it for the RMS speed. And I'd just start with this 1/2 MVRMS squared. This formula is on the sheet anyway that I'm developing, but it's good to see where it comes from. Then multiply both sides by 2 and divide by m, and you'd get V RMS squared is equal to 3KT over 2m, and that's just a couple algebra steps. And then just take the square root of both sides, and the RMS speed is going to be the square root of 3KT over m. Okay, over 2m, excuse me. Oh, wait. Was that 3/2 case of BT? It may be. It probably was, and trying to do it from memory. So that should have been over a 2. And I think we have a 2 here, and if there was a 2 there, then we'd end up with 3KT over m. But I'm not positive. I need to call up the formula, which I had done before I had to reboot my computer because it was misbehaving. Let me open up the formula sheet, and we'll switch the view to that so we can see it. Let's see, thermodynamics test formula sheet. Everything is slow. Okay, I'll change the view up to that formula sheet to make sure I've got that. Oh, is it 3/2 or 3? Alex, I bet it's 3/2, right? But I wanted to check out that formula sheet just to make sure. And yeah, I'm pretty sure. I want to zoom in on this. And somewhere down here, heat capacities. Oh, it's under the Maxwell-Boltzmann distribution. By the way, this F of V dV thing is something that we didn't look at. Some years we do, but this one we didn't. Okay. I don't have the formula for the kinetic energy, or do I? Yeah, I don't see it on here. That's weird. Okay, that's something I need to add to that before I give it to you tomorrow. Anyway, it's 3KT over m is what the VRMS would be. So I did remember it right eventually. Now, the hard part here is calculating m because it's a nitrogen molecule. So what do we do about that? Well, here's the thing. A nitrogen, for any atom or molecule, virtually all of the mass comes about because of the protons and neutrons. And a nitrogen molecule has 14 protons and 14 neutrons.
We're still on the formula sheet.
Whoops. Okay. Yeah, I'll come back to here. Okay. There we are. New share. Back to here. Okay. Anyway, a nitrogen molecule has 14 protons and 14 neutrons. Each of the protons and neutrons have with an average mass of about 1.67 times 10 to the minus 27th kilograms. So the mass here is going to be 14 and 14 is 28. 28 times 1.67 times 10 to the minus 27 kilograms. And that's the mass that'll go in here. So I'll end up taking a square root here. 3 times Boltzmann's constant again. 1.38 times 10 to the minus 23 times the temperature, and it has to be the Kelvin temperature, 375 Kelvin. Oh, that's joules per Kelvin is the units on the Boltzmann's constant, and then 375 Kelvin, and divide by the mass that I'm going to get by doing that. And I don't know how you might be taught in chemistry, but this is a way that works just fine. If all you're worried about is three significant figures. Now, it's not going to give you the exact mass of a nitrogen molecule, because something that we're not including is the mass of the electrons. And we're also not using the binding energy of the atoms and the binding energy of the molecule. If you wanted a much more precise thing, you'd have to include those, but this is good enough to 3 sig figs anyway, so we'll just go with what we've got. So 28 times 1.67, and it's 4.68 times 10 to the minus 26 into the minus 26 kilograms. Now, that's not actually a good unit of mass to use for these things anyway, but it's okay, because up top we'll have joules per Kelvin times Kelvin. Those will go away. Then we've got a joule per kilogram, but a joule is a kilogram meter squared per second squared. And so the kilograms go away. Under the square root, we have meters squared per second squared, but when you take the square root, you get meters per second, which you'd expect for a speed. And I'm just kind of curious how fast these things are going. 375 Kelvin, that's about 100 Kelvin above the boiling temperature of water, or 102. So they may be going at a more than 500 meters per second, maybe. So we could estimate real fast. Let's see. Have 10 to the third left on top. Yeah, we'll have a reasonably big number here anyway. Square root of. If I don't get something that's a few hundred, I'd go back and check my work, because that's okay. I get 576. So that's a pretty good clip. But these things are tiny, so that's why they can be going so fast. Would we multiply the mass by 2? No, there are 2 nitrogen atoms in the nitrogen gas. And I set up here the nitrogen molecule contains 14 protons and 14 neutrons. The nitrogen atom has 7 protons and 7 neutrons, but the molecule has 14 of each of those things. So that's what would happen there. If while you're taking the test tomorrow, if you have a question like that on it, don't hesitate to ask me, because I know this molecules and atoms and moles and things like that are unfamiliar to some of you. So if you'd ask it, then I'd write up on the board whatever it was that your question had, or whatever the answer to it happened to be. So that's okay. Okay. Were there any other questions on this thing? Well, we've got this kind of sample test. This was the test that I gave the week after March 13th, 2020, when we were suddenly told that from here on out, everything was online. And that was finals week for that quarter, which was, I don't know, kind of weird. Anyway. Problem 5 on here. Okay. Okay. On a nice day at the surface of Mars. I wrote this problem one year. It was 2008, and there was a student in the class that quarter who Don't know if she ever became, well, as far as I know, she isn't an astronaut yet, but she did major in astrophysics at the University of Washington. And I had her name written into this thing when we did it. That was back in the years when we had tiny classes. There were only 4 students that quarter, and for the spring quarter as well. Anyway, nice day on the surface of Mars. The atmospheric pressure is 605 pascals, and that is not a typo. The atmospheric pressure on Mars is about 0.6% of what it is on the surface of the Earth. And the temperature is minus 30 degrees Celsius. So an astronaut celebrating her birthday decides to do an experiment. She fills a balloon with helium inside the habitat where the temperature is blah, 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 and blah, and then takes the balloon outside and assume it's at the same temperature and pressure as the inside of the habitat before it's taken outside. If the pressure inside the balloon matches the outside pressure at all times and the initial volume is 5 liters, determine the volume of the balloon when it reaches equilibrium with the Martian atmosphere. Okay, well, here's something. The temperature outside the habitat is a lot colder than the temperature inside, so that would tend to make the balloon shrink, but the pressure outside is only 650 pascals, so there's much less pressure pushing in on the balloon, so it can expand against that. And it's kind of a fight against that, but it's actually the pressure difference that's going to have a bigger effect than the temperature difference. And this turns out to be an ideal gas law problem. You may not recognize it, but it is, and that's the method to solve this thing. It's helium, so it behaves very much like an ideal gas. And the ideal gas law is PV equals nRT. And your sample of gas is contained inside a balloon, so that's not going to change. By the way, we could also have this as PV equals capital N K sub B times T, Boltzmann's constant times T. Either one would work because I'm going to get rid of those constants in here. And T has to be in Kelvin. So here's what we have for P initial. P initial is inside the balloon. It's 1.01 times 10 to the 5th Pascal. And a Pascal is a Newton per square meter. The initial volume of the balloon is 5.00 liters. Now, those may not be convenient, but the way I'm going to solve the problem doesn't matter. We're going to make all the units divide out. So almost all of them, except the final volume won't. And then T initial inside the habitat. The temperature is, I think it said 20.0 degrees Celsius, which would be take the Celsius temperature and add 273.15, and you'll have the Kelvin temperature. So you'd actually get, let's see, 293 point, we could say, well, we've only got one sig fig. So I'd call this 293.2 Kelvin. And we don't actually, we can kind of do it here. So that's the initial conditions. The final conditions, P final is equal to those 605 Pascal. V final is what we're after, so that's a question mark. And T final is the temperature outside the habitat, and it's minus 30 degrees Celsius. Add the minus 30 to 273.15, and you would get 273 minus 30, 243.2 Kelvin. So we've got more sig figs on the temperature than we do on anything else. So I didn't really need to keep track of all those, but it doesn't hurt. Now, here's the way I solve these things. When it's a problem like this, I'll go P initial, V initial is N R T initial. I could figure out how many moles of gas are in the balloon or how many particles of gas are in the balloon. This would be NKT, not NRT. Case B. But I don't need to, and I'll show you why. I'll have P final, V final equals NRT final. And I should have written these in the opposite order, but what I'm going to do is divide this equation by that one, because I don't care about the N and the R. I just want to know what the final volume is. So I'll take the bottom equation, divide by the top one, P initial, V initial, N R T initial. And I do a lot of ideal gas law problems this way, where I just set them up with the initial and the final conditions, divide one equation by the other, and the things that I don't care about, the number of moles, divide out, and the things that'll actually determine what's going on here, I hang on to. So I can take some ratios here. One is V final over V initial is going to equal, well, on the right side, I've got T final over T initial, whoops, divided by T initial. And I'm going to divide by P final divided by P initial. So I've got those things, and then I can just multiply out from underneath by the V initial. So V final will equal, okay, T final over T initial, that's 243.2 Kelvin divided by 293.2 Kelvin. So that numerator would tend to make it shrink, but the denominator, which is P final over P initial, is 605 Pascal divided by 1.01 times 10 to the 5th Pascal. This is going to be a really small number that we're dividing by, so that's going to blow this thing up. And then I multiply it by V initial, whoops, which was 5.00 liters. And so I didn't have to convert those liters into cubic meters because all the units divide out here, and I'm taking a ratio of things, so I'll get the same units that for V final that I had for V initial. And whatever it turns out to be, kind of curious. And I get, this thing's probably going to pop before it gets here. I get about 69.2 liters for the final volume of the balloon. And since it was 5 to start with, 69 is what, about 14 times as big? Unless it's a really good balloon, it's probably going to pop long before it gets there. So even though the air was getting a lot colder and it should have shrunk, it didn't. If you ever blow up a balloon and stick it in the freezer, you can see that they shrink when they're in there. Okay, let's see, that was number 5. Also have a request for number 4. Let's see, we have a glass flask for which the volume is 1000.00 centimeters cubed at 0 degrees Celsius, is filled exactly level with mercury at that temperature. And when the flask and the mercury are heated to 55.0 degrees Celsius, 8.95 cubic centimeters of mercury spills out of the flask. If the coefficient of volume expansion for mercury is 18 times 10 to the minus fifth degrees Celsius, determine the coefficient of volume expansion for the glass. Okay, well, here's the formula for volume expansion. It happens to be delta V is equal to, in this case, it would be beta V delta T. And that formula should be somewhere on the formula sheet. I'll switch over to there really quick, but I'll try to remember to come back to this. Anyway, I think that would be on the top of this column. Yep, there it is. Delta V equals beta, okay, V naught delta T. That was the original volume of the thing. So that's the formula anyway. So I can put a sub-zero there. Okay, well, there's going to be a delta V for the glass and a delta V for the mercury. And we can calculate the final volume of each one of those things. Delta V is actually...
We're still on the formula sheet again.
Okay, I'll get you back. New share, back to this thing. Okay, there we go. Anyway, the delta V is V final minus V naught. So we could say that V final is going to equal V naught plus beta V naught delta T. And you can also write this as V naught times 1 plus beta delta T. And maybe that might be easier, we'll see. And I'm going to set up an equation like this for both the glass and the mercury. It looks here like the mercury, since it spills out of the flask, that tells me that the mercury probably has a higher coefficient of volume expansion than the glass does. So for the mercury, let's see, Hg, is that the chemical symbol for mercury? I can't remember. Chemists, help me out here. Somebody type into the message thing, whatever that one happens to be. But anyway, for the glass, or for the mercury, I think it's hydrangeum or something like that in Latin, liquid silver. But it would be V final for, I'm going to guess that it's Hg, even if it's not. Pretend it is, if it's not. That's going to equal. The V naught for the mercury happens to be the same as that for the, it is Hg. Okay, it's the same as that for the other stuff. So I can just, I'm just going to use V naught and let off to the side. V naught is 100.00 centimeters cubed. And as long as I use the same units, it doesn't matter. So that'll be 1 times 1 plus beta for the mercury times the delta T, which in this case is, it's at 0.0 to start with, and it's heated to 55. So delta T is 55.0 degrees Celsius. So I have that. And then there's V final for the glass, chemical symbol Gl, and that's going to be the same V naught as mercury, but I'd have 1 plus beta for the glass times 55.0 degrees Celsius. So between those two equations, I should be able to figure this thing out. And this is bigger than that one by 18.0, no, that's not what it is, by 8.95 centimeters cubed. So V final for the mercury minus V final for the glass. Now it's just an algebra puzzle is all we've got going in here. But that's the 8.95 centimeters cubed will equal V naught for the mercury. And maybe I'll just expand each of these things. I'll have, because actually the first V naughts are going to drop out. I'll have V naught plus V naught beta for the mercury times 55.0 degrees Celsius minus, I'm subtracting one from the other, V naught minus V naught beta sub glass times 55.0 degrees Celsius. And the V naught, these V naughts go away, but I still have those V naughts there. So if I bring this down, I would have 8.95 centimeters cubed is equal to, let's see, V naught beta Hg times 55.0 degrees Celsius. This is all numbers that I know actually, minus V naught beta for the glass times 55.0 degrees Celsius. And let's see. I could factor out the V naught or divide out the V naught. And so I could divide both sides, 8.95 centimeters cubed divided by 1000.00 centimeters cubed. And those are going to divide out for me. But that will equal what's left behind is beta H sub G times 55.0 degrees Celsius minus, whoops, no more V naughts, beta for glass times 55.0 degrees Celsius. And I think if I bring that over, beta for the glass times 55.0 degrees Celsius is going to equal this thing. And I'm going to plug in a number for that now. Beta for the mercury is 18.0 times 10 to the minus fifth per degree Celsius. Times 55.0 degrees Celsius. Whoops, that's per degree Celsius on that thing. And then I'd subtract this, which is, I think, 8.95 times 10 to the minus third times 10 to the minus third. So I need to do this subtraction before I divide by 55 degrees. So then I get a really small number over here. Let's see. Actually, that's got three significant figures on it. Although I bet I don't when I subtract them. I should have calculated this by itself. Yeah, this thing here ends up being 9.90 times 10 to the minus 3 minus 8.95. So let's see, what did I get there? Oh, I got 9.5 times 10 to the minus fourth. I only have two significant figures left. Times 10 to the minus fourth, then this is dimensionless. But if I divide that by 55 degrees Celsius, I'd get beta for the glass is equal to and I'm down to just two significant figures. It's 1.7 times 10 to the minus fifth per degree Celsius. And how does that compare? Actually, it's only about a tenth of what the volume expansion for mercury is. So the glass doesn't expand as much as the mercury on that one. Okay, any questions on that one? Also had a request for problem number 6, wherever that is. From, let's see. Okay, there we go. I hope you've got these in front of you. I don't know if you'll be able to read them on the thing or not. Although I am experimenting with I rotated my monitor and I'm trying that, and people thought it was a little clearer. Anyway, 1 mole of an ideal monatomic gas is taken through the cycle shown in the graph below. The process AB is an isothermal expansion, and that means the temperature stays the same throughout this AB here. Assume 3, so we don't have to do a calculation on this, so that's okay. Anyway, without doing any calculations, determine the sign of the 3 quantities listed below for the entire cycle, A to B to C back to A. Oh, for the entire cycle. Okay. In each case, explain your reasoning. Well, delta U, if you start at some point, pressure and volume, that also fixes the temperature. And starting at point A, going down to B, going back to C, and then coming up to A, the change in internal energy, that's what delta U is 0 for any complete cycle, unless you discard some of the gas along the way, but you're taking this gas, the entire 1 mole through the entire cycle, the internal energy won't change. So delta U, the sign of delta U for the entire cycle is 0 because delta U or U only depends on temperature. And you're returning to the state, the same state. Okay, so that one was not so hard to calculate actually, but you did have to know that delta U is the internal energy, and it only depends on the temperature. And if you start at some point and come back to the same point on the PV diagram, you are returning to the same state, the same temperature, the same pressure, the same volume. For an ideal gas, PV equals nRT. So if you come back to the same PV value that you had to start with, the temperature is going to be the same as well. N is the number of moles and R is that gas constant. So there's no change. For the work, now for that, you have to know that for any thermodynamic cycle, the work is going to be the integral of the pressure. It's PdV for that part of the cycle. Okay. Well, that makes it the area under a PV curve. And I'll do a couple extra drawings here, but this will be the same diagram that we've got here. But if we consider first this isothermal expansion from A to B, the work that's done by the gas during that part is going to be this volume. If you just drop from A and B straight down to the V axis here, it'll be this area here. Okay. So that's positive. And then for the part when you're going from B over to C here, so here's B and here's C, you're going in this direction. It's a decrease in volume, but you still have a positive pressure, but you're headed in this direction. And the magnitude of the work done in this part is this little square here, which would be the same as, or rectangle, same as this little rectangle here, but it's negative. However, in magnitude, it's smaller than the work that was done from here to here. And so far, we've got a large amount of positive work that was done from A to B, and a small amount of negative work that when you add those together, you'll still have a positive amount of work. And then you go from C to A, but the work done on any cycle is the integral of P dV, and from C to A, there is no change in volume, so there's no work for that. So here's what we've got. We've got the work from A to B. That's positive and big. We have the work from B to C. That's negative and small. And we have the work done from C to A is 0. And when you add all these things up, you'll have positive and big added to negative and small. Okay, positive wins out over negative. And so you'll end up with the work from A to B to C back to A is going to be positive. Okay. Okay, well, that's the first two. Then for Q, that's the amount of heat that had to flow into this thing for this entire cycle. However, there's a shortcut. We don't even have to consider the individual parts of it, because for an entire, actually for any cycle, the change in internal energy is Q, the heat flow into the system, minus W, the work done by the gas or by the system. Well, for that cycle, we've got delta U is equal to 0. So delta U is equal to 0, and that's equal to Q minus W. And the sign convention is that Q is for the heat flow into the system. It's positive if heat flows into the system. W is the work done by the system. And so it's positive if the system does work. But and that's what we have here. Anyway, Q is just going to equal W, because Q minus W is equal to 0. So it's positive for the entire cycle. So this is a first law of thermodynamics problem, is what that one happens to be. Okay. Are there any other ones? I don't know what else we had. Let's see. We had that additional problem. I can't remember if I did that one. I did do that one in class. I'm not sure why I stuck it on there. Yeah, there's a recording of me doing that problem somewhere. I'm guessing that you guys are probably pretty good at doing that, because I think just about everybody on the homework assignment did the problem related to a dual pane window correctly, and I was happy to see that. Oh, I had a question at the top of the chat. Okay, let me scroll back up. Oh, didn't I do the first added problem in the thing? Wasn't that the first added problem, Alex, or not? Or Alyssa? Oh, can I walk through the topics of the test like I normally do? I'll post this thing tonight somewhere. I had topics for the thermodynamics test, but they've had a lot of things that won't be on this one, but I'll track down that file and go through it anyway. Oh, let's see, gotta get my mouse character back on this monitor. Um, okay, let me switch the view again. Here we go. Okay, hopefully you see something like Physics 222 thermodynamics test topics. And start off with, no, I can't write on this thing. I guess I could print it. Yeah, maybe I'll print it. That might be the easiest way. Then I could scribble on it while we're doing this. However, temperature and thermal equilibrium, there's a zeroth law of thermodynamics that someone quoted on their homework assignment. I was kind of happy to see that. If you have three objects like A, B, and C, if the temperature of A is equal to the temperature of B, and if the temperature of C is equal to the temperature of B, then the temperature of A is equal to the temperature of C. That's that's the zeroth law of thermodynamics, but oh shoot, I could have blown this up, I guess, but maybe I should have. I'll do that. Control A and bump up the font about a whole bunch. Yeah, I'll print that off that way. Then you can actually see what I'm doing. And there are some things on this sheet that you won't be tested on, so I'll cross those out. Okay, these hopefully are big enough to read. Celsius to Kelvin temperature or conversion. I hope you know by now that if you're given a Celsius temperature and you need the Kelvin temperature, the T in Kelvin is just the temperature in Celsius, but just the number of it, plus 273.15. And I think that formula is on the formula sheet. So thermal expansion, linear and volume, they both look alike. For linear, you'd have the change in length is equal to alpha L, or maybe L naught delta T. And alpha is the coefficient of linear expansion. And then for delta V, it looks just like it, except it's beta instead. Beta V naught, this time delta T. So those probably aren't a big deal. Quantity of heat, we use letter Q for that. Heat capacity. Heat capacity is something that's usually molar heat capacity, and we didn't do anything with that until we got to gases. But usually we deal with specific heat, which is the energy required per unit mass to raise the temperature of something.
If you're writing on the paper right now, we can only currently see the
Okay, the blown up one. All right. It's my usual thing. Okay, where am I? I'm on the visualizer. Something weird about this is the icon keeps moving around for that. I don't know why. No. Anyway, heat capacity. This is the heat energy required, or the heat required to raise the temperature by some temperature, would equal MC delta T. And C is a number that depends on the substance, whatever it happens to be, and it's joules per kilogram Kelvin is what it usually is expressed in. And then you'd be given the mass in kilograms and the delta T if you're told that. You can figure it out. Or sometimes you're given the temperature change and you're supposed to figure out what Q was. Or sometimes you're given Q and you're supposed to figure out what delta T is. But that's that stuff. Phase changes, that's if something is going from, say, a solid to a liquid. In that case, the energy required is the amount of mass times it's called the heat of fusion. And there's no temperature change because you'd have it at the melting temperature as a solid, and then you melt it and it becomes a liquid at that same temperature. So it's just looking like that. Or if you're changing something from a liquid at its boiling temperature into a gas, then you have the amount of mass of stuff and you multiply by the heat of vaporization. And those are things that have been experimentally determined, and you have to look them up in a table, or you'll be given them for the problem, whatever it might happen to be. And as far as mechanisms of heat transfer, we just talked about convection and radiation, or I did, but we didn't do any calculation with them. So you don't have to worry about those two, although you always hear about conduction, convection, radiation, or maybe you've heard about that stuff, but we were only concerned calculation-wise with the conduction, and that was the rate at which heat flows through something. Conduction you can think of as it happens best in solids, but it also goes on in gases and liquids. It's more efficient in solids, and you can think of it as atom to atom contact. If you have a spoon and you stick it in a pot of boiling water, say a metal spoon, it's a long metal spoon. Imagine that it's a great big thing that you've got in there and sticking out of the handle, sticking out of the water, but the end of the spoon that's in the boiling water will get heated because molecules of the boiling water will smack into it, and they get the molecules in the metal spoon bouncing together and vibrating as a result. And then metal on the outside layer, those atoms will bounce into atoms on the under the outer layer, and it's just an atom to atom collision thing, a chain reaction of sorts that just goes on. And that's what convectivity is. We were interested in calculating the rate of heat flow, and that was the H equals dq dt. And it, for the ones we did, it was some constant of thermal conductivity times the area of the thing, and then times the temperature difference, T hot minus T cold. So it flows from the hot side of whatever the material is to the cool side, and it's inversely proportional to the length. The longer the thing happens to be, the slower the heat will flow through it. And so that was that. Ideal gas equation, this is PV equals nRT. This would be and I also had a different version of this where I used the capital N. Lowercase n was the number of moles, capital N is the number of particles themselves, and with this version, we use Boltzmann's constant times the temperature. But it's the same thing as what you're doing. To get from the number of moles to the number of particles, you take the number of moles and multiply by something called Avogadro's number, and that's 6.02 times 10 to the 23rd particles per mole is what Avogadro's number is. It's on the formula sheet, and that would equal the capital N. And then if you take the gas constant and divide it by Avogadro's number, you get Boltzmann's constant. So there's that link between the two. And it just depends on what you're most interested in seeing. I did a problem where we were looking at the number of particles per unit volume in some nebula or other. I can't remember which one it was now, but for that, we wanted to use the PV equals N case of dt. And so we did. Okay, kinetic molecular model. We did not do anything with the Maxwell-Boltzmann distribution. That's on the formula sheet, but which I still don't think I printed off here. Anyway, it's on there. Some years we do. It turns out that describes for particular temperatures, it'll tell you the probability of a particle having a speed between V and V plus dV. So it's a probability distribution is what it is. But some years we do calculations with it, and I have students show from that distribution that the law for the RMS speed, or the 1/2 mv/RMS squared, is 3/2 k sub bt. I'd have them show using that distribution that VRMS is 3 kT over m. And this distribution is something that can be more or less derived from the principles of quantum mechanics and things like that. It's kind of fun. Okay, heat capacities of gases and CV and CP. We did not do anything with the heat capacity at constant pressure. And I pretty much just dumped C sub V in your lap. That C sub V is 3/2 R for monatomic gases. Whoops, monotonic. And it's 5/2 R for diatomic gases. And where those show up is that the amount of heat required to raise the temperature of a gas by delta T is number of moles times C sub V times delta T. And then depending on the type of gas you have, if it's monatomic or diatomic, you'd use either 3/2 R or 5/2 R. And that was about all we did with that. And then we barely introduced the first law of thermodynamics and the work done by a gas. First law of thermodynamics is that the change in internal energy of a gas in any process is the heat flow into it minus the work that's done by the gas. And this is just a statement of conservation of energy. And that's all it happens to be. So if you have the gas doing work and you're not putting any energy into the gas at the same time, you'll actually have a decrease in the internal energy of the gas because it takes energy to do work and it comes from the internal energy. If you're pumping heat into a gas, but maybe you're fixing the volume so it can't do work, then the internal energy will go up. And it turns out that the internal energy of a gas depends only on the temperature. So that's something that we have. We did not talk about paths between thermodynamic states. There are different kinds. There's isothermal processes. The temperature stays the same. Adiabats That's a process that takes place so fast that there's no time for heat to flow into it or not, or it's in an insulated container. There's constant pressure and constant volume, but we didn't talk about that. So don't worry about that. And cyclic processes, we just did a problem with that. In any cyclic process, the change in internal energy is zero. So depending on the cycle, you might be able to figure out Q and W for the cycle as well. Actually, it's easiest to figure out on a PV diagram. And then let's see, we've got heat capacities of gases. We didn't do anything with C sub P. We didn't do anything with that. And we didn't do anything with that. So that's pretty much it. This was a fairly short unit. Okay, there's one new message in here that I can't see. Got a question at the top of, oh, Alyssa, a question at the top of the chat. Let's see. The green one. Can I walk through the test like I normally do? All right. I'm just seeing initials and I'm not thinking of you as initials. I'm usually thinking of names, but sometimes I can figure it out. Let's see. I had a question for Juan. Are you in student government? And if so, what's your office? Public Relations Office. Okay. My daughter was in student government when she was a student here. That was 20 years ago. Wow. But anyway, she was the secretary, I think, of so she had to go to meetings and take minutes or something. But it paid tuition, I guess. Plus at that time, you got money that you could buy books at the bookstore or anything you wanted. And I have a Big Ben sweatshirt that she got me. Okay, any other questions? Okay, I'm planning on starting the test right at 2:15 and you should be out of there by 3:30. I'll give you 75 minutes for this one, even though I don't think it'll be too long a test, but that'll let you think hard about everything. I'll try to give you plenty of room so people who like to fill pages with writing and calculations on things will have enough room to do it. Okay, it's 9:30. I think I have to take the dog out one more time and then see you all tomorrow. And I'll probably be there a little bit early tomorrow. So if you have any last minute questions, you could ask some then. Okay, you're welcome. I haven't mentioned this enough, but this is actually the best class percentage-wise I've ever had, as far as everybody doing very well on the tests. I'm just kind of amazed. Rumor had it that people who went through COVID were, I don't know, a ways behind, but I'm definitely not seeing that with you. So I'll see you tomorrow. Okay, how do I get out of here? I want to stop the share, end the meeting for all.